Uh, okay, am I audible? Am I audible?
Yes, sir.
Okay, okay, fine. So yeah, so what I'm planning for today's session is I'll briefly discuss, have a quick brief discussion regarding the contents of week 12, and then as we decided, we'll be revising week 6 to week, let's see, week 9. So since nobody uh, posted any comment on YouTube, so I'm assuming it has any objection to the suggestion that was raised yesterday. But yeah, as this will be the last session of this series. So the contents of week 12 that were covered were following. The transistors for electronics and for RF electronics. Uh, they discussed. Is my voice breaking? Uh, can anybody, can anyone else confirm it if my voice is breaking?
Oh, okay, sir.
It's okay, right? Probably there is some issue with your end. So yeah, then we discussed transistors for RF and memory, and then basics of microelectronic fabrication was covered. Okay, so yeah, now brief recap. So transistors, various applications. Yeah. These include, uh, yeah, I mean, you have class of transistors for memory devices. Uh, what else applications are there? The
Sir,
transistors.
you are discussing 12 week.
Sorry,
Week 12.
I'm
You
not
are
getting the
discussing
point.
you are discussing week 12.
Yeah, actually, I'm planning to discuss briefly week 12 and then we'll proceed as per the plan. The plan was to revise few weeks, right? And I'm aware of that. I mean, I'll do that. Just that I want to briefly discuss week 12 for the sake of continuity.
Okay, sir. Okay.
Now, okay. So applications include memory devices, right? Memory devices, what else? Class of transistors are they targeting which application? Memory devices, what else? High speed logic, right? Then we have just let me know if I get disconnected from audio. So you have this, right? Memory devices, high-speed logic, and then you have transistors that target power switching. Okay? Power switching, say power electronics. Right. Then you have uh, RF, right? RF electronics, right? Transistors that target RF electronics, right? Say also, I mean, power amplifiers, transistors that target this particular medium. Then we have low noise amplifier, right? Then we have sensors or say phototransistors. Okay? So memory is there, high speed logic is there, power switching, RF electronics, LNA, sensors, phototransistors. So broadly, application areas that different transistors target, right? And the crux of this week 12 content was to know which kind of transistor is used in which application, right? I mean, what kind of transistors are used in memory, what kind of transistors are used in high-speed logic, similarly power switching, RF electronics, low noise amplifier, sensors for the transistors. Okay, and also you were supposed to, uh, sorry, is there any question?
Sorry, sir. Sorry, sir.
Okay, probably. So now also, uh, I mean, you were supposed to know what does it take for a transistor to qualify for a particular application, right? What are those qualities that qualify the transistor for a particular application, right? Uh, so yeah, these were the two things that I broadly discussed in week 12 content. And yeah, for example, what kind of transistors target the power switching and power electronics? They don't have gain, okay? The transistors that are used for converters or that are used in power switching, they don't have gain. Right? And what we do is we ground the source and we sweep the drain voltage from 0 to whatever. So no, I mean, yeah. First point is that we don't actually write it. We don't have gain. Okay? And I mean, switch, it has two states, right? For the switch, you have on state, and then you have off state. Correct? And what about this? When the switch is in on state, does it allow high current to pass through it or low current to pass through?
High current, sir.
High current, right? And similarly, what happens in off state is it blocks
High
a large
voltage.
voltage, right? I mean, this high current and high blocking voltage capability are ideal characteristics for a switch, right? For example, if you are, I mean, if the switch is rated, 1 ampere, 100 volts, it means that has an on current carrying capability of 1 ampere, and it can block at max 100 voltage in our state. Okay, so that is one thing. And also, how do you measure breakdown of a transistor? A method, or I should say, a measurement was described or shown. Right? Three-terminal breakdown measurement. Right? So what happens in three-terminal breakdown measurement? What is the measurement process? You have a following structure. You have source, you have drain, 10 volts. This is grounded. Okay, somewhere here. This is a gate, right? And then you have barrier. Like him. Okay. Yeah. Do that here. And what is the current flow path? This. Okay. That's how the drain current flows in this structure. So now, what will happen if I apply a negative gate voltage? This is 2
There
decay.
will be there will be vacant
What
space.
will happen? What will happen to the channel?
There will be depletion.
The channel will be depleted. Right. Okay. Uh, this is so far I'm audible, right? So as you said, when we apply a negative gate voltage, it pinches off the channel, right? And when it pinches off the channel, the charge that is below gate is depleted. So this charge would be depleted, right? is depleted. Okay. Now we then make sure that the channel is completely depleted by applying a suitable gate voltage. Okay. And then what we do is we ground this source. Okay. I mean, did you got the point? First of all, we ensure that this is completely depleted. Okay. And then we ground this source and drain we sweep. Drain is swept. We sweep it from say 0 to some particular voltage, say V drain. Fine. And then what do we record is? We record ID. Okay. ID is recorded. So these are, suppose get this ID. And it's usually in picoamps or nanoamps. Right. And this is your ID. We also measure this I gate. Okay. I gate would be this. Okay. So this is I gate, this is I drain. Suppose and also I mean, there would be a point when this device goes into breakdown, right? A very large drain current or very large gate current flows. So we record that point. That would be the breakdown voltage, right? And yeah, that is, and this breakdown voltage would be known as three-terminal breakdown voltage. Uh, the name comes from the measuring technique, right? This is a three-terminal breakdown measuring technique. So this breakdown that you would get, suppose you get 100 volts, right? At which this current flows up. So then you would record that voltage and that would be your breakdown voltage, three-terminal breakdown. Okay, so this is one thing that I wanted to discuss with regards to week 12. Now comes the revision part. So which week should we revise? Let me know.
Start with the 5.
Didn't we cover week 5 yesterday?
Yes, sir, you can cover.
Right. So should we go
6,
for
7
6 now?
is
Should I
possible, sir.
start? Okay, I'll start with 6 then. Okay. So, okay. Now we will be revising week 6. Okay. So in this week, in that week 6, we were introduced to transistors. We were introduced to BJT, right? And basics of BJT were discussed. Working of BJT, the delays in BJT, all things were discussed. Now, so question number 1, what you were asked is in a uniformly doped BJT, assume that your NE, NB, and NC are emitter based and collector doping in atoms per centimeter cube respectively. If the emitter injection efficiency of BJT is close to unity, which one of the following is true? Right. So this is your emitter injection efficiency. Right. This emitter injection efficiency gamma is IEP by I. Right. And yes. So this is typically the order, right? In our BJT, this emitter
The
doping
doping
is,
concentration.
yeah, I mean, doping order is like this, right? Emitter doping is higher, then comes base doping, and then collector doping, right? And
But, sir, I think collector is moderately doped.
Collector is
Base,
moderately doped. No, I mean this is the order as far as I remember. We can double check that. For a PNP transistor, this would be the order. Okay.
sir,
And
actually, if you consider doping with respect to area,
okay,
then this is okay, sir.
what do you mean by considering doping with respect to area?
Actually, sir, I consider that the number of carrier available with respect to per unit area.
You see, doping has units of concentration, right? It would
Yes.
have units centimeter raised to the power minus 6, right?
Okay. Yes, sir.
So that is what I've written here, right? So doping would be in atoms per centimeter cube respectively. So now, and
Okay, sir.
the order would be NE would be greater than NB would be greater than NC. So the other important information that was given in the question was that your emitter injection efficiency of BJT is close to unity, right? So that means your gamma is unity. Gamma is IEP by IE, right? And you can write that gamma in terms of doping. It turns out the expression would be NE by NB plus N. This I had left as an homework, but I did not receive mail as to how do you come from this to this. So if anybody is interested, you can still mail me since we are
Sir,
discussing it again today. Yeah,
can I try, sir?
you can try, sure. I
Sir,
mean,
actually,
do
sir.
one thing. Let's not try it in this session because today's session is not that long. So,
Okay, okay,
and we
okay,
won't
sir.
be able to otherwise touch questions. So what you do is, uh, I'll leave this again as a homework for today. Do one thing, do this and let me know. I mean, how do we write this gamma in terms of this? Okay. So now, assuming that you can write this in terms of this, right? And this is unity. When will this be unity? Is when this NE would be sufficiently greater than NB, right? So this is the order it has to follow. This is fine. Why this is right?
Yes, sir. Yes.
Okay. Just give me 5 minutes. I mean, I'll charge my buds. Let's start. So we finished this question, right?
Yes,
Then
sir.
was this question number 2. What was asked in question number 2 was to find this base transfer factor. Okay, the DC current gain beta was 50. Right? I mean, this particular info was given that your beta is 50. Now, assessing that your emitter junction efficiency is 0.9995, right? I mean, this and this is given, and you have to compute this base transport factor. Now, your base transport factor is given by what? What is the base transport factor by definition? It is, I mean, it's there on this slide. It's ICP by IAP, right? And uh, emitter injection efficiency is this gamma. We already touched this here, right? IEP by IE, and beta is IC by IB. What is beta? The DC current gain, simple. And
DC current gain, sir, in common emitter mode.
sorry,
Beta is DC current gain in common emitter mode.
yeah. I mean, that is what I'm saying. I mean, here it would be IC by IB, right? In that mode. So now we are aware of this equation, right? I is IC by IC plus IB, right? If I divide throughout by IC, I mean, I'll end up reaching here. Can I write this? I can, right? 1 by alpha
Yes,
is
sir,
equal
yes.
to 1 plus 1 by beta. And then if I take the reciprocal, I can end up with this alpha is beta whole divided by 1 plus beta. And I can write this as gamma times B, right? Now focus here. If I take product of this and this cancels out, right? And I'm left with this ICP by I, right? This is what I wrote here. And that is by definition alpha, right? Because alpha we saw is 1 times B. So I can write B as 1 by gamma times alpha, and alpha is beta by 1 plus beta. I mean, are you able to follow how I arrived at this?
Yes, sir.
What I'm doing is I'm simply taking this gamma here. This would be 1 by gamma, and this would be the B. That is essentially this. And your beta is your, what's say, DC current in that is 50, and beta plus 1 is 51, and gamma is your emitter junction efficiency, that is 0.999. We are done with this. That is your base transport factor. And it comes about as 0.98. Okay. Now, for BJT, the common base current gain alpha is 0.98. Okay, alpha is 0.9. And the collector base junction reverse bias saturation current ICO, that is 1 microamps. Now, this BJT, okay, so for a BJT, uh, you have this as the common base current gain and this as the collector base junction reverse bias saturation current ICO, that is 1 microamp. Now, this BJT is connected in common emitter mode and it's operated in active regime, right? Where the base drive current IV that is equal to 20 microamps. The collector current IC for this mode of operation is what? So you know this IC is alpha times IE plus ICO. What is ICO? ICO is that base reverse by saturation. And then I can write IE as IC plus IV. Right. If I then take IC on the left-hand side, this would be 1 minus alpha. And then if I divide out by 1 minus alpha, this would go here, it would be 1 minus alpha, 1 minus alpha. That is what I wrote, right? And then what we need to do is just substitute this. Alpha is this 0.98. We substitute that. IB is what? 20 microamps. We'll get the collector current as 1.03 milliamps. Is that fine?
Yes, sir. What about the drawing, sir?
What about what? About?
About the drawing,
Okay,
why
you
you
mean
draw
this?
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 Yes, sir. Yes, sir.
Okay, so this is common base configuration, right? And in common base configuration, alpha is IC by IE. You know this, right?
Yes, sir. Yes.
And why I'm writing this and this is because, see, we were given a BJT that had a common base gain, right? And this BJT was connected is connected in the common emitter mode, right? So in common emitter mode, the current gain is IC by IB. So that's why I draw both the configurations.
Okay, sir. Okay. Thank you, sir.
Okay. You can again watch this particular lecture. Which lecture is this? Sixth, right? So there I would have discussed it in much detail. In
Okay,
this, we would try to finish as many questions as we can. Because actually this extra session was supposed to be 1 hour. I mean, or maybe even less than that. So that's why I'll try to finish it quickly. So now consider two BJTs that are biased at the same collector current with area A1. Okay, tell me one thing. Did other TAs agree to this for revising some weeks?
yes, sir. Yes, sir. In
Okay,
another
so
another sir, in another course,
yeah,
one TS sir revise the first 4 weeks, sir.
no, no, don't tell me about other course. I'm talking about this particular course, Fundamentals of Semiconductor Devices. We are three TAs in that, right?
Yes, yes.
So I'm talking about the other two TAs. What
Yes,
did
sir. Sir also means
Okay, sir.
one of the sir is sir
Okay,
IIT
fine, sir.
Bangalore.
okay
He can take revise from 8 weeks up to weeks, sir.
up to 8 weeks?
Means from 7 to 8, 7, 8, 6 weeks he can revise.
First 7, 8 weeks.
No, no, directly 7, 8,
7 and 8. Okay. Then
and three
probably I
weeks
should.
also.
Okay. Uh, Do one thing. I can at least cover 6 or probably touch 7. And whatever is left, you can communicate to him, and accordingly, he can
Okay,
try
okay,
to
sir. Okay,
finish that. If that is, if he agrees to that, it's his personal decision. So now, consider the two BJTs that are biased at the same collector current with area, uh, this area, right? 0.1 micrometer and 0.1 micrometer. And A2 is 100 micrometer times 100 micrometer. Assuming that all the other device parameters are identical, KT by Q is 26 millivolts, right? The intrinsic carrier concentration is 10 to the power 10 per centimeter cube. Q is 1.6 times 10 to the power minus 19 coulomb. The difference between the base emitter voltage in millivolts of the two BJTs is what? This is what you're supposed to know. What you're supposed to compute. Delta VB, right? So IC is beta times IB, and our IC is this, right? A times, this is area of cross section. This is reverse saturation current density JS, exponential of VB by VT. This equation you know about IC, right? So uh, we have to equate the two, right? Why do we need to equate the currents? Because it's given that has the same collector current. It's just that the areas are different. Areas and JS are different. Are you getting the point?
Yes, sir.
Yeah. So currents are same. So now when currents are same, and I know the expressions, right? Expressions, I write 1, 1, and 1. Similarly, I write 2, 2, and 2, and then I'll equate it, right? This and this would go, right? And I'll be left with area, right? And uh, area is known, right? A1 is, will multiply this by this in micrometer square. That would be your A1. Similarly, have your A2. If you put in the calculations, uh, you'll arrive at this. That difference between the base emitter voltage would be, I mean, are you getting the point? I mean, you have to first rearrange them. You have to
Yes, sir.
take
Yes.
this exponential here, and then it would be exponential of VBE1 minus VBE2 by VT. I mean, I'm assuming that you know those steps, right? Once you do that, you will land up with this, that VB1 minus VB2 is VT ln of 10 to the power 6. And if you simplify that, it comes about as 360 millivolts. Okay,
That 10 to the 6 will be A1,
10 to the,
A2 by A1.
what would be 10 to the power 6?
A2 by A1, sir.
Yeah, it would be, right? See, it's, what is A1? I need to take
A1
A1
is
here, right? So I'll write A2 by A1.
0.01, sir.
What is A2? A2 is 100 times 100,
Yes.
and we have 10 to the power minus 2. If you'll see, this will go up, and we'll have 10 to the power 6 factor.
Okay. 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 Okay.
What's the point? That's why it's 10 to the power 6 here. So yeah, I mean, that was how you get, let's say, 15 millivolts. Then we have this problem in an NPN BJT that's having a reverse saturation current IS 10 to the power minus 15 amps. That is biased in forward active region with VB equal to this particular voltage. Right. And the current gain, it may vary from 100 to 150 due to manufacturing variations. The maximum emitter current in microamps is what? See, IE is IC plus IB, right? If you take IC common, you'll have 1 plus IB by IC, right? And IC by IB is 1 by beta. Sorry, IC by IB is beta, and IB by IC would be 1 by beta, right? So
Yes, sir.
what we had to compute was what? We had to maximize this, right? In order to maximize this, we had to minimize beta. So IE max would occur corresponding to beta minimum. And the minimum beta value that it can take is 100. Once you substitute that and you put VBE as 700 millivolts, because we know the expression of this. What is expression for IC? IC you can write as IS times exponential of VB by VT, where this IS is this 10 to the power minus 15. Correct?
Yes, sir. Yes, sir.
So once you plug in the values and compute the corresponding current, you'll have this particular value, 1460 microamps, which would be 1.46 milliamps. But since we were asked to compute the current in microamps, so we'll leave it here. This is fine.
Yes. Up to, sir, fine.
Okay, now then we have the next question. The injected excess electron concentration profile in the base region of an NPN BJT, that is biased in the active region, is linear. Okay, so this region is linear, as shown in the figure. If the area of the emitter base junction is this, we have the mobility, the base region as this, the depletion layer widths are negligible. So we have to compute IC at room temperature. See, I is nothing but A times J. And what is J? J you can write as QDN delta N by, uh, sorry, dou delta N by dou X. This is A, right? Because it's in centimeter square. What uh, I remember I mentioned this or raised this point there is I try to express everything in terms of centimeters for unit consistency, right? So this was already in centimeters square, so I'll keep it like this. This is charge 1.6 into 10 power minus 19. dn is 0.026. No, I mean, how I have computed dn, I've utilized Einstein's equation, right? Because d by mu is kt by q. This particular is what? 0.026. Mu is 800 centimeters square. Since this was already given in centimeters square, I did not change it. So I multiplied kt by q with mu to get dn. Is this fine? This particular would be dn. Is it fine?
Yes, sir. Up to that point.
Okay. And then we had this particular quantity. So how uh, I mean, wrote this is as follows. So this is nothing but slope of this, right? And if I divide this by this, I'll get this. Won't I?
10 to the 14 by 0.5
Yeah, 10 to the power 14 by 0.5. 0.5 what? This is 0.5.
micrometer.
Yeah, but I have to convert it into meter or
Centimeter.
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 Centimeter. Why? Because I mean, I took everything in terms of centimeter. For unit consistency, I had to do that. Other approach would have been I had to convert this into meter, this into meter. Then also it would have been cancelled. But it's better to work in terms of centimeter in electronics. So that's why I converted this into centimeter, right? So here, this what uh, this zero point 0.5 micrometer would be 0.5 to 10 to the power minus 4 centimeter. And once you put this in the calculator, you'll have this particular value. The I is 6.656 milliamps. Fine. I hope this is clear.
Yes, sir. Yes, sir.
And then this was one liner that base width modulation results in increase in the output conductance of the device. And yeah, then we have this particular question. So you can consider the uniformly doped silicon BJT that has the following specs, right? Uh, you have been given that this metallurgical base width is 0.5 micrometer. Okay. Base doping is 10 to the power 16 per centimeter cube, obviously. Punch through voltage is 25 volts. Assume that VBI is very, very less than this punch through voltage. And we had to compute the collector doping concentration. What is XD? XD is here. What is XD?
Sir, X is the depletion width.
Yeah, it is a depletion width. Just give me a second. Okay. Just give me a second. Okay. Hello.
Yes, sir.
Okay. Okay. So what was I discussing? I was discussing that here this base width is zero point 0.5 micrometer, right? And that is XDB plus XDC. This is XDB, this is XDC, right? Sum of these two, right? And if you take XDB common, we'll be left with this 1 plus XDC divided by XDB, right?
Yes, sir.
And then what? Wait. Yeah, I mean, this is from the charge balance side. XDB times doping in the base is XDC on the collector side. Right? If depletion width on the collector side times. What is this doping?
Collector doping, sir.
Correct. This is the collector doping. So then it turns out that I can write XDC by XDB as NB by NC. I can write it like this, right?
Yes, sir. Yes.
So what is? So this would be NB by NC, right? And XD is this, right? Is XDB 1 plus NB by NC. Now, 1 plus NB by NC. I can write XDB as this. I mean, I have to take this factor there, but it would be in reciprocal. So it would come like this. XDB is XD times NC divided by NB plus NC. Then I write this,
Yes, sir. Yes, sir. Simple division,
correct?
sir.
Yeah, this is simple division. So you know this. I mean, this was a formula that you were supposed to know, right? This simple depletion width formula of a PN junction. We can open your notes and see the formula. What is the formula of this uh, depletion width of a PN junction in case of bias, right? Here bias would be the base collector voltage. So you have this, right? So what were you supposed to compute? Collector doping concentration. Can you compute it? You can, right? Reason, I punch through your this XDB, right? This would be your entire this base width, metallurgical base width, right? And that particular base width is given. That is 0.5 micrometer. I mean, we'll utilize that, right? I'll put VBC as 25 and I'll replace this XDB by WB. Note I'm taking this factor inside. How I'll do that? I mean, XD was this, right? And I have this factor. If I take this inside a square root, I'll have to square this. Remember last time? So I need
Yes,
to
sir. Yes.
square this in order to take this here. Once I do that, I'll end up with this. So then this simple, this I'm substituting the value. Again, here it was 0.5 micrometer. I'll write 0.5 to 10 to the power minus 4 centimeter and then square that. Then this is simply here, right? And here the only unknown would be NC. Why? Because base doping is given. So once you know the base doping, you'll only be left with this NC that is unknown. Rest of the things all are known. So your NC would be 8.38 into 10 to the power 14 per centimeter cube. Please make it a habit of writing everything in terms of centimeter, right? While evaluating concentrations or any quantity of electrons. It would be handy and useful. So then now in the last question, what is the depletion width of the collector? Since we knew this and uh, XDB we computed, right? Did we compute XDB? Okay, if we consider the case of 0.3, yeah. So XDB was known, NB was known, collector doping we found out, so XDC can be computed. So you can simply do the maths. What would
Sir,
be XDC? Sorry,
where I can find the XT, sir?
XDB,
Where I can find the XT? I can find the formula of XT.
this formula.
No, 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 sir. Actually, I in last problem, I find the XB formula. Value how?
Can you please again come clearly? I'm not able to hear. I think either it's problem with my audio or the problem at your end. Repeat again your query. Hello,
Hello.
Somnath. Yeah,
Yes, sir.
please
Am I
repeat the question.
No, sir. In last problem,
In the last problem, yeah,
I can find the formula of the in that
I can find the formula of what?
XGB. XGB. Here.
This,
Yes, sir.
yeah.
No, sir.
Then
But
what?
I
This,
how can I find the value of XGB?
how you can find out the value of XDB?
Where is
Okay.
value is given?
See, what you would do is we'll consider the case of punch through. Fine. We'll consider the case of punch
Yes,
through.
sir. Yes, sir.
If you consider the case of punch through, then what would be your XDB? This. That was given, zero point 0.5. So that you would
Okay,
substitute
okay,
here and find out
okay.
what this. Fine. Yeah, because see, the thing is, the doping would see. The point was when I used XDB as metallurgical base grade, I got a particular NC. This NC is not random, but a function of this VBC. Are you getting the point? Had I chosen
Yes, sir.
a different VBC, right? Suppose it
Punch
was
to
not
cannot
punch through.
happen.
Yeah, then I would have accordingly got a different value of this and a different value of NC, such that this equation is still satisfied. This will hold true, whatever be the case. Are you getting the point?
Okay. Yes, sir.
That is effectively how it gets handled and manipulated. So yeah, this was left as an exercise. You can try this out. And if you have any query or doubt, you can let me know on mail. So that finishes week 6. Will he cover 7th week?
Yes, sir. Yes, sir. If your time permits, sir.
No, let's do one thing. What do you want me to cover in week 7? Let's quickly go over through week 7 and I'll repeat the portion that you want me to cover. Okay.
Okay, sir.
Although, I mean, this was probably the easiest one because it was essentially MOSCAN. Right. So, what did we discuss here? We discussed regions of operations right here. Right. The first case corresponded to accumulation, in which the gate voltage is negative. Right. The second case corresponded to the case of depletion, right? When your VG is positive but still less than VTH. Keep in mind this is NMOS, right? Because your substrate is P type. So, so the channel would be formed of electrons, right? And similarly, when your gate voltage is greater than the threshold voltage, your VG and your VG is positive, that would correspond, which is this case. The region of
Inversion.
operation is inversion, correct. And how do we define this threshold voltage? So then the point or the discussion we headed towards was about this VTH, right? At VG equal to VTH, your surface potential is 2 phi, right? Your surface potential is 2 phi. So what happens is, since it is the case of NMOS, so it's P type. So the Fermi level, see, your Fermi level, where would be this Fermi level for a P type?
Near to conduction bed, sir.
It would be near to valence band, right? Since it's P type.
So for P type, sir.
Yeah, right. For P type, it would be near to this,
Yes.
right? When you apply a voltage, a sufficiently high voltage. So the point is, at the surface, uh, there would be some doping in the bulk, right? Na,
Yes, sir.
right? And I can say that your P is Na. Would you agree? Would you agree if I write P is equal to Na?
Due to, sir, in case of less number of minority here, sir, what will be the majority carrier will be replaced by Na.
Correct. So P is Na. What is electron? That would be Ni square by Na. So that is pretty small, right? Because it's
Yes,
P-type
sir.
substrate. Electrons are minority. So when you invert the channel, what happens is the concentration of the electrons becomes sufficiently high, such that even that becomes Na at the surface. Are you getting the point? Because what are we doing? We are modulating the concentration of electrons at the surface. That is the whole point of this
The
line
last
bias.
sentence.
Okay, I'll repeat the last sentence. This is a field action, right? When you apply gate voltage, you are essentially modulating the carriers, right? Which carriers? The carriers that are there at the surface dominantly, right? I mean, they will experience change majorly. So when you increase the gate voltage, the electrons would be drawn, right? And a point will come when the concentration of the electrons would increase so much that it would be equal to Na. Suppose Na was 10 to the power. Let me take an example. Suppose Na was 10 to the power 50. Is it fine?
Yes, sir.
Or it was P, right? What is the concentration of electrons?
Now, sir, it will be, sir, 10 to the 5.
Good. Would be 10 to the power 5. So now, and this 10 to the power 5 was at surface also, right? It's throughout. It would be 10 to the power throughout. Are you getting it? It's uniform.
Yes,
But
sir.
when I apply gate, I'm essentially modulating the concentration of electrons at the surface, right?
Yes, sir.
So I'm increasing that when I am applying a positive gate voltage for a P-type substrate MOSFET, or I should say NMOS. So it increases the concentration of the electrons at the surface, right? So it increases from 10 to the power 5 all the way till 10 to the power 15, right? The
Yes,
moment
sir.
it touches this 10 to the power 15, right, this would be corresponding to some value of gate voltage, right?
Yes, sir.
That particular voltage value of the gate would be the threshold voltage. That is how it's defined. So in terms of surface potential, this is how it manifests.
Okay, sir. Okay.
Okay. We take any standard textbook. Uh, we can
Sir,
probably take
IS
which.
indicate,
Sorry, I mean,
IS,
can you repeat
sir, IS indicate that
this?
strong threshold.
This size.
Yes, sir. Yes, sir.
This size is surface potential. Yeah.
This is
Yeah.
the for strong
Yeah.
inversion case.
You can consider. Yeah. This is the strong inversion. Beyond this, it's strong inversion. This is the point at which that strong inversion. Fine.
Okay, sir.
Yeah. And since phi f we knew is kd by q ln of Na by Ni, this formula is handy. I mean, try to memorize it. That phi f is nothing but kT by q ln of Na by Ni. Okay.
Okay. Okay.
Then what? Okay. Then we had a band diagram that was given of a p-type semiconductor of a band gap 1 electron volt. A student was asked to fabricate a MOS using a below semiconductor such that it has the following parameters. Right, your VTH was 0 - 0.16 volts. Your Cox was 100 nanofarad per centimeter square. Metal work function was this. I guess I won't repeat this. You can probably watch my that week lecture. This was week 7, right? Week 7 lecture. And if there is any doubt, you can contact me.
Okay,
Right?
sir. Okay.
And then regarding this, what is the value of phi ms? For phi ms, you need to take the difference of phi m and phi s. Right? What is phi m? Phi m was given probably, right? This is phi m. Phi m is nothing but metal work function. That is 3.87 electron volt. Right? What is phi s? We need to take this difference from vacuum all the way till this curve. And this is your phi s. Here it's 4, then it's 4.5. If this is 0.2, this has to be 0.3. So it's 4.8. Would you agree?
Yes, sir. Yes, sir.
right? Because this is the mid of the band gap. So this has to be zero point 0.5. If this is zero point 0.5 and this is 0.2, this has to be 0.3.
Point three.
So 0.5 plus zero point 0.3 is 0.8. Add that to 4, that's 4.8. That is what I wrote. Take the difference, that would be
Okay, sir.
what? 0.93, and that is the value of IMS. And then, yeah, this particular question you can again refer to the week 7. This would take uh, more time, so I'll leave this. I mean, let's do one thing. If you have any doubt whatsoever regarding week 7, you can reach out to me on mail. Okay. Otherwise, we'll probably lengthen the session a lot. If possible, do one thing. Watch my this week 7 session on 2x speed, playback 2x. Right? These all are recorded, right?
Okay, sir. Okay.
Okay. I mean, actually, I have some little work to do. That's why. I mean, otherwise, I would have done as promised.
No, sir. No
You
issue, sir.
can you can let me
Thank
know
you, sir.
via email. I'll try to address any query as much as possible, but try to come up with queries within 2-3 days. Okay, because otherwise, then you'll have to prepare for the exam as well, right? When is the exam? It's 14th April right now.
Sir, 40th April is exam.
No, I'm telling 14th April. It's today is 14th April, right?
Okay, okay. Exam will be, sir, on 25th.
25th. Yeah, that is what I'm saying. Try to uh, watch these lectures quickly uh, and ask me questions over mail uh, within 3 days, and then you'll have a barrier of or a buffer of 1 week to revise. Is this fine?
Okay, sir. Okay. Okay, sir.
Okay.
Thank you,
Okay,
sir.
fine. Thank you. Thank you.
Thank you, sir, for
My
dealing with
pleasure.
us, sir.
No, no, it was pleasure. I mean, I really enjoyed. I mean, this was, uh, I would say, more interactive than uh, last course that I took last semester. So yeah, thanks to you all for making it interactive. So bye bye.
Okay, sir.
If
Bye, sir.
there is any query, even a non-technical query, you can reach out to me. Any particular feedback that you would like to provide? I mean, I'll not mind even if it's negative.
Sir, I just tell me two sentences that uh, you three are the fabulous, sir.
I
You
should.
three years, you 3 years are, sir, excellent, sir.
Okay.
Because, sir, whenever we can ask some questions, the level of thought will be beyond ground. But still now
I
you are
guess I
not facing
probably
any.
I probably did not get your point. I mean, are you talking with regards to timing? The timing
No, no,
should
no,
be
sir.
flexible. Then
I just say that, sir, your patience level will be extraordinary, sir.
okay. I got that.
Whatever questions we are asked, sir,
Mhm.
this is beyond ground level. But still now,
I mean, that is how we learn, right? I mean, we learn as well from those questions. It's not about the patience only. We get to learn as well because when different students come up with different questions, there is something to learn.
but sir, I just give you some compliment
Okay.
that
Thanks for that.
that
Thanks for that.
your teaching quality will be sir, different for because I am also teach in a private college.
Okay.
So, sir, whatever you can teach, sir, and whatever way you can deliver, you can thought, sir, multiple way to understand the thing better.
Thank you. Thank you so much. It really means a lot.
Okay,
Thank
sir.
you.
Bye, sir.
Okay, bye. Any other feedback from other students, or should we call it a day?
Thank you, sir. Thank you, sir.
Okay. Bye bye. Was a
Bye,
pleasure
bye,
to
sir.
have you.
Bye, sir.
Bye. Bye.